Hello students, welcome to our lecture. I am Assistant Professor Gayatri Kharat from Shri Mudhai Devi Shikshan Sanstha, Professor Sambhajirao Kadam College, Deur. Course BSc 1, Semester 1, Subject Physics, Paper number 2nd, Electricity and Magnetism 1. Our today's topic is Magnetostatics. So let's start. Our first point is magnetization. So here all materials are made up of tiny particles called atoms. Atoms are composed of negatively charged electrons that rotate around the nucleus of atom. The electrons in the atoms of magnetic materials are spinning in the same direction around the nucleus. So, definition of magnetization is when a material is placed in a magnetic field, the atomic magnets align partly or totally in the direction of applied magnetic field. This process is called magnetization. Magnetization refers to the process by which a material acquires a magnetic moment when placed in an external magnetic field. It represents the degree to which a material can be magnetized. Magnetization is denoted by capital M. M equal to magnetic dipole moment divided by value. But magnetic dipole moment equal to current into area. Therefore, capital M equal to current into area by volume. The SI unit of intensity of magnetization is ampere per meter. Magnetization is uniform if the substance is homogeneous and isotropic. Here the types of magnetic materials. There are three types of magnetic material. First one is diamagnetic, second one is paramagnetic, and third one is ferromagnetic. In diamagnetic, weakly repelled by a magnet field. Second, in paramagnetic, weakly attracted to a magnetic field. And third is ferromagnetic. In ferromagnetic, strongly attract and retain magnetization even after the external field is removed. Magnetization curve and hysteresis loop. Initial magnetization curve shows how magnetization increases with the applied magnetic field. Hysteresis loop. In hysteresis loop represent the lag between magnetization and the applied magnetic field. It explains the residual magnetism in materials. So our next point is dielectric medium. In dielectric medium, insulating material that does not conduct electricity but can be polarized when placed in an electric field. It plays a crucial role in storing and reducing the strength of electric fields in capacitors and the other electronic devices. This is the dielectric medium. Now, here some characteristics of dielectric medium. First characteristic is non-conductive. In non-conductive, it does not allow free flow of electric charges. Second one is polarizable. It can develop electric dipoles in the presence of external electric field. The third characteristic is increases capacitance. A dielectric material placed between capacitor plates increase the capacitor's ability to store charge. This is all about characteristics of dielectric medium. Our next point is types of dielectrics. First type is polar dielectrics and second type is non-polar dielectrics. In polar dielectrics, molecules have a permanent dipole moment. Example is water. Then non-polar dielectrics, molecules do not have a permanent dipole moment but develop one external electric field. The example is oxygen and nitrogen in non-polar dielectrics. Here next some applications of dielectric medium: capacitors, transformers, insulators in electrical circuits, microwave devices. Effect of dielectric in a capacitor. When a dielectric material is placed between the plates of a capacitor, first point is the capacitance increases by a factor of the dielectric constant. Second point is the electric field decreases inside the capacitor. The third point is the energy stored in the capacitor increases. So our next point is Biot-Savart's law. This is very important law. Biot-Savart's law states that the magnetic field at a point due to small element of current carrying conductor is first is directly proportional to length of the element and second is directly proportional to current flowing through it. Third is directly proportional to sine of the angle between the element and the line joining the center of the element to the point. Fourth is inversely proportional to square of the distance of the point from the center of the element. And the derivation of Biot-Savart's law is B bar equal to mu naught by 4 pi integration of I dl bar cross r bar divided by r cube. Here some applications of Biot-Savart's law. First application is magnetic field due to a straight current carrying wire. Second application is magnetic field at the center of a circular loop. Third application is magnetic field due to a solenoid. B equal to mu naught by 4 pi I into 2, then B equal to mu naught I divided by 2 pi r. Here value of B is same for all points at the same distance from the long straight conductor. Thus the lines of magnetic field are circles concentrate with the wire and lying in planes perpendicular to it. Next point is magnetic vector potential A. A magnetic vector potential A is a vector field used to describe the magnetic field in region of space. It is useful concept in electromagnetism for simplifying the calculation of magnetic field in various situations. Definition of magnetic electric field is: the magnetic vector potential is defined as a vector quantity whose curl gives the magnetic field. We know the well-known vector identity is del bar cross del bar into A bar equal to 0, where A bar is an arbitrary vector, that is the divergence of any curl is 0. Hence we can write the magnetic vector potential is B bar equal to del bar into A bar. Thank you.